When Elon Musk gave the world its first look at Terafab, most people focused only on the factory's insane scale and capacity: 100 million square feet and 1 terawatt of AI computing capacity per year, equivalent to producing roughly 100 to 200 billion custom AI chips and memory units annually. But there's one detail in Tesla and SpaceX's Terafab design that most people may have overlooked. It's a gigantic circle located right at the center. Elon Musk emphasized on X that Terafab will be 50 times the size of the Pentagon when complete. He also left 6 letters FELFTW, hinting at what happens inside that enormous circle. Over the next 10 minutes, you're going to be stunned by the truth behind Terafab's central circle, and by how Elon Musk may be unleashing the biggest change to the semiconductor industry in decades. As we all know, Tesla is no longer putting all its focus on revenue from electric vehicles. Instead, the company is betting its future on Optimus robots and robotaxis. Meanwhile, SpaceX wants to expand Starlink and bring AI into space. But all of these ambitions share one major weakness: AI chips. Right now, Tesla can't simply order as many chips as it wants. Supply from manufacturers like NVIDIA, TSMC, and Samsung is still limited. And according to Elon Musk, the amount of AI chips the world is currently producing may satisfy only about 2% of the potential demand that the Tesla and SpaceX ecosystem could generate. This is no longer just a typical chip shortage. It's a problem with the manufacturing capacity of the entire semiconductor industry, and that's exactly why Terafab exists. Elon Musk is reportedly targeting a facility spanning roughly 100 million square feet, equivalent to about 10 times the size of Gigafactory Texas or 15.4 pentagons. Based on what has been revealed, Terafab is envisioned as an integrated system where chip logic, high-speed memory, advanced packaging, and numerous other manufacturing processes could all be carried out within the same complex. But scale is only the most visible part of the story. Very few people are actually paying attention to how Terafab plans to manufacture its chips. Elon once described an extremely fast feedback loop: create a photolithography mask, manufacture the chip, test the chip, modify the design, create a new mask, and repeat the process. Instead of sending designs between multiple companies and different fabs, everything could potentially happen inside Terafab. And if you think that's already ambitious enough, take a look at the giant circle in the center of Terafab. Specifically, one ex-user examined the blueprint and asked Elon whether there was a particle accelerator underneath the circle. Elon Musk responded with 6 letters: FELFTW. In other words, free electron laser, for the win. So, what does this actually mean? We'll try to explain it as simply as possible because most people basically assume that manufacturing a chip is easy. That may have been true for older generations of chips, but it's no longer the case for the cutting-edge AI chips Elon Musk wants to build. One of the biggest bottlenecks in advanced chip manufacturing is EUV, or extreme ultraviolet lithography. You can think of it this way. To create smaller transistors, chipmakers need extremely short wavelength light to print incredibly tiny structures onto silicon wafers. Today's EUV systems use light with a wavelength of around 13.5 nanometers. The problem is that generating that light is anything but simple. Current EUV machines use a high-powered laser to blast tiny droplets of tin. The tin is converted into an ultra-hot plasma, which then emits EUV light. The technology works, but it consumes enormous amounts of energy and generates debris that can potentially damage the incredibly expensive mirror systems inside the machine. That's where free electron laser at Terafab could be a game changer. Instead of using tin, a free electron laser uses free electrons accelerated to nearly the speed of light. These electrons then pass through a specialized array of magnets called an undulator. As the electrons are forced to oscillate, they emit light. With precise control, these light signals can interact coherently, producing an extremely powerful, clean, and tunable beam of light. In theory, it could generate exactly the kind of EUV light the semiconductor industry needs. And more importantly, if this could be achieved at industrial scale, the impact could be enormous. Why? In a conventional chip fab, each EUV lithography machine needs its own dedicated light source. That can become a bottleneck as production scales up. For Terafab, with a target of hundreds of thousands of wafers per month, the problem becomes even more significant simply because of the sheer scale. Based on what we've found, a centralized free electron laser source capable of supplying EUV light to multiple lithography systems could transform the light source from a bottleneck within each individual machine into shared infrastructure serving the entire fab. This would eliminate the need for each system to struggle with its own dedicated light source. There would be no more constantly firing tin droplets that generate debris, and in theory it could deliver higher power, better energy efficiency, and much greater scalability. That's exactly why that giant circle could be so important. But ultimately, Terafab may have another card to play that could make the entire concept of that circle truly viable. And that card is Intel. Building an advanced semiconductor fab is completely different from building a car factory. A 2-nanometer fab, or anything more advanced, requires ultra-clean environments, EUV systems worth hundreds of millions of dollars, extremely pure chemicals, and atomic-level precision. One tiny defect can ruin an entire batch of wafers. Tesla has experience with large-scale manufacturing. SpaceX has experience with rapid optimization and iteration. But Intel has decades of experience operating advanced semiconductor fabs. That's why Intel's involvement in Terafab could be far more significant than simply having its logo attached to the project. Terafab also has another advantage. It recruited Gary Jiang, a former Intel manufacturing executive with 17 years of experience, as the project's first director. He previously oversaw Intel's 18A manufacturing operations. With an expected total investment of $119 billion at full scale, Elon Musk isn't simply throwing money at a chip factory. The Tesla CEO is attempting to assemble an entire system that brings together capital, scale, AI, manufacturing, and semiconductor expertise. So where will a factory this massive get its power? Clearly, running a 100 million square foot facility designed to support 1 terawatt of AI compute per year would require an extraordinary amount of electricity. But SpaceX has brought a major surprise to Terafab. According to the latest information from Grimes County, SpaceX, the company leading the project, plans to build its own power infrastructure for Terafab rather than rely entirely on Texas's public power grid. Specifically, SpaceX says it plans to build natural gas-fired power plants combined with very large battery storage systems. That means Terafab is being designed not just as a massive chip factory but potentially as a self-powered industrial ecosystem, giving SpaceX much more control over the enormous and continuous energy demands of semiconductor manufacturing. Notably, the current plan does not mention using solar panels or Tesla's solar power systems, even though Tesla is one of the key companies behind Terafab. That creates a pretty interesting contrast. Tesla is famous for its electric vehicles, Powerwall, and especially Megapack, its grid-scale energy storage system. Many people might have expected Terafab to become a showcase for renewable energy at massive scale, but the reality appears to be heading in a different direction. The primary power source will be natural gas combined with large-scale battery storage, and the reason for that decision is actually very practical. An advanced semiconductor fab can't simply have power when the sun is shining. It needs what the industry calls firm power, a stable, continuous electricity supply that can operate reliably with virtually no interruption. Imagine a factory with billions of dollars worth of equipment running 24/7. A single major power failure could disrupt production, damage wafers and equipment, and potentially affect the entire manufacturing process. Meanwhile, solar power is inherently intermittent. It can generate huge amounts of electricity during the day, but not at night. Weather conditions can also change. And when Terafab is targeting electricity demand on an enormous scale, relying solely on solar plus batteries could require a massive and extremely expensive storage system from day one. That's why natural gas gives SpaceX something incredibly important: control. By building its own power plants, SpaceX wouldn't have to wait years to get connected to the public grid. It could have much more control over the project's timeline. It could also avoid putting additional pressure on the local grid and reduce the risk of Terafab having to compete for electricity with the other AI data centers popping up across the United States. And here's a very important detail. Energy is now becoming a bottleneck just as significant as chips. AI needs GPS, GPS need chip fabs, but chip fabs and data centers need enormous amounts of electricity, so the AI race is no longer simply about who has more chips. It's becoming a race to see who can secure the chips, factories, and energy the fastest. According to the initial plans, once Terafab begins production, it could start at around 100,000 wafers per month, with a long-term goal of reaching 1 million wafers per month. If it reaches that scale, this would no longer be a fab built solely to serve Tesla. It could become one of the largest semiconductor manufacturing hubs on the planet. Terafab is reportedly expected to create at least 3,000 jobs in the surrounding areas of Texas, while the first phase alone would require approximately $16.8 billion in capital investment. And if all planned future phases are eventually built out, the total investment could reach as much as $119 billion. That figure would make Terafab the most expensive project Elon Musk has ever built, surpassing every major project he has undertaken before. Tesla needs millions, even billions, of brains for Optimus. Cybercab needs the computing power to drive autonomously. SpaceX needs chips for Starlink and AI systems in space. XAI needs ever-increasing computing capacity to develop more powerful AI models. All of these ambitions share the same weakness. Without enough chips, everything is limited. Instead of continuing to rely entirely on external supply chains, Musk is trying to build the manufacturing capacity he needs himself. That's why Terafab could be far more important than its 100 million square foot footprint suggests. Tesla doesn't need Terafab simply to sell chips. It needs those chips to create an entirely new ecosystem of machines and AI. AI-5 is planned to power full self-driving, robo-taxi, and Optimus, followed by AI-6, AI-7, and future generations. Meanwhile, the D3 family is being developed for Starlink and AI applications in space, where chips must withstand radiation, extreme temperatures, and the vacuum of space. Those are the two chips that will transform Tesla and SpaceX. So if that $119 billion truly creates chip manufacturing capacity on an unprecedented scale, just how much will Terafab disrupt the semiconductor industry? That's the end of this episode. If you love seeing how Tesla turns bold ideas into real plans, leave a like and subscribe. We'll keep uncovering the engineering that powers the future.